Hello everybody, welcome to another data analytics video. Today we're going to talk about the predictive investment modelling system that we worked with the Queensland Fire Emergency Services back in 2018-19 and go through with all of the other partners that we worked with that as well, and give you a good understanding about what the project was about, what we did, and how it potentially could be used in pretty much any organisation in the world that doesn't know with 100% certainty what's going to happen in the future, which should be everyone. Alright, so what was the situation? Essentially, the new QFES, or Queensland Fire Commissioner, Katarina Carroll, had said to the head of strategy, I need to know where and when to invest over the next 10 years, and I need to know it soon, because we need to know what sort of extra fire trucks, or they call them fire appliances in the Queensland Fire and Emergency Services, we might need, not just how many, but what type. We also need to know if we need any new fire stations, or whether we need to upgrade any fire stations, or even possibly to retire some as well. We need to know that. We need to know about the people, how many of them we need, in what locations, what skills they need, when they should be on duty during the day or the night, or whether they should be on call, what training we need to be giving them over this next 10 years, whether they should be full-time, part-time, casual, or we should be relying more on our volunteer workforce in the rural fire areas and the state emergency services. Also the equipment. We need to know about whether or not where the equipment should be located, so it's very quickly available for the specific problems that we might be reacting to. And on top of that, we need to know about how much effort it's going to take to keep that equipment functioning, and people having the knowledge to use it, which is what capability is really about. It's the integration of all of these equipment and tools and capabilities and people all together, so that we can actually respond to service demands that actually come down the pipe. So, and it's not, as I was saying before, it's not just where do we need them, but when do we need them, because the world is changing. The population's moving into new areas, they're growing, which means that the service demands are coming from new places that they weren't coming from before. The amount of those service demands is changing, and with changing things like the number of cars on the road, and the types of cars and how safe they are, those change things like road accidents and similar things with regards to earthquakes and so on. And in fact, it's important to have a look at the kinds of things that QFES responds to. So everyone obviously thinks about structure fires like house fires and things like that, and obviously we need to keep in mind that as Queensland's structures get older, they become more prone to fire, and they are obviously being constructed all over the state, so where they are is changing, and it's not just households, there's also factories and those other kinds of structures. There's good old bushfire, which is something that up until a couple of years ago, in fact it was 2000 and just after we put this model forward, which is a bit of a story about that, but bushfires was something that had caused devastation down in Victoria and New South Wales in previous years, and Queensland up to that point in time had yet to have a really major bushfire season where that major destruction was. There's plenty of bushfires, but not to the level that New South Wales and Victoria had seen in the past. But that was possibly going to change due to things like climate change changing, as well as the incursion of residences into areas that they weren't there before. So the bushfire is more likely to impact people. Obviously, cyclones is something that's a pretty important issue in Queensland. It actually makes Queenslanders pretty disaster ready, but at the same time, that means that we need to be up and running for those cyclones as well. Tsunamis, haven't had a major one since Queensland became fairly populated, but it could happen. We've all seen what happened in Japan So we have to be ready for those, because who's going to respond to that? Well, QFES is the primary respondent to something like that. Obviously, earthquakes is similar. We had earthquakes in Newcastle, not yet anything major in any major residential area in Queensland yet. Obviously, we've had earthquakes, but nothing that we've needed to have a major response to. But that may change, and we've got to be ready for those, even if it's never happened before. Obviously, a terrorist attack is another thing that we have to be ready for. And back when we were doing this particular project, it was pre-pandemic. So terrorist attack was very much on everybody's mind, and we were wanting to make sure that QFES was able to be ready for that as well. So changing landscape, the world's changing, and all the things that I'm talking about there are completely under anyone's control. They could happen at any time. The type of disaster could be different. The severity of that disaster, where it hits, who it's affecting, all those things, no one will know what's going to happen. So we have to be ready for a great range of potential problems. So that makes it tough. Where do you invest your fire trucks? Where do you put your people? Where do you put your equipment? So that's basically what Katarina Carroll was asking the strategy leads, which is why they then came to data analytics and the Department of Housing and Public Works to ask what could we do. So we did decide to come up with an approach that would address this using 3 streams. We only had 14 weeks to come up with the initial approach. We wanted to make sure that we were able to come up with our suggestions via an objective method rather than subjective, political persuasion. The loudest and the creakiest wheel gets the oil type approach of giving over operational capital budget over that 10-year period. We wanted to bring some objective evidence into it. So we thought what we do is have a go with these 3 streams. So I'll go through each stream and explain what they do. So stream 1 started off with the hazards. So what hazards do we have? What is their likelihood? Where are they more likely to occur? And how is that going to change over the entire 10 years? So we wanted to come up with a probability of a hazard occurring in any one location across the whole of Queensland. So we basically went on to 3,653 days, I should say. There's actually 3 leap years during that period. Over 540 SA2s in Queensland, with the probability of the hazard occurring within that particular SA2 on each day. Now, obviously, cyclones occur more during the summer and less during the winter. Bushfires, similarly. Things like road accidents don't change, but they do change in terms of the holidays versus working days and things like that. So all of those things have different probability distributions, and they change over time in different ways. Obviously, all of those will change over the period of the 10 years as well, as climate change comes through, as more cars go on the road, and those kinds of things. Exposures, so that's basically the people and the assets and the houses that are in place at the moment, and then they are being changed as well. So how vulnerable they are is another issue. So some of those assets might be older. They might be in areas that are more prone to getting fires or earthquakes or whatever. And then there's people that are in those structures and assets that are also at risk, and those populations are changing. People are moving from rural areas to urban areas. Some of those urban areas are growing quite quickly, so we need to be able to handle all of the changes over time. So that also has 10-year forecasts in there. So that's what this stream 1's mainly about, is forecasting. So then we move over to stream 2. I probably should just go back a little bit and just talk about, so stream 1, obviously the point was to come up with the forecasts, but how did we do that? So obviously we tried to utilise forecasts that already existed as much as we possibly could, but where we couldn't, we tried to use the data that was available to us, and I'll go through some of the data available a little bit later. But then we used essentially machine learning algorithms and statistical algorithms to do those forecasts, and then utilised where we couldn't do that sort of thing. We used expert opinion to come up with what we couldn't come up with objective data. But at least we weren't asking them where we should put the assets. What we were doing was asking them to come up with reasonable assessments of exposure changes and hazard changes over time. So objective data wherever possible, forecasts that are then sense checked by experts, and then where all of that's not available, we've used experts to come up with our forecasts. All right, so now we're moving into Stream 2. Now what Stream 2 is doing is mapping all of those probabilities into a 10-year stochastic or probability-based scenario of service demands that Queensland Fire has to respond to. So obviously this is several hundred thousand, something like 700,000, 750,000 per year. Per scenario, and that QFES has to respond to. But not only did we have to come up with the service demands themselves, so fire at 10 Boab Street, Elanora, but we also had to say how serious it was, and if there was any complications such as inclusions of hazardous materials. We also had to go across a wide range of potential service demands, including traffic accidents, poison spillage, or hazardous material spillage, fast water rescue. There was many different service demands, and they too have a different probability depending on the hazard being exposed over the exposures, so that the vulnerability of those exposures driving those service demands. So we had mappings for all of that as well. But once we came up with one scenario, that's not necessarily sufficient to be able to come up with all the various ways that things could change. So we thought we better do some more. So we did a second one, we did a third one, in fact we did 1,000. So in order to come up with 1,000 scenarios, with each with 750,000 service demands, so we're talking 750 million overall service demands that were being generated out of our stochastic model. Obviously we're talking several terabytes of data that we're having to generate, and that obviously had big significant impacts on how we do that generation. Now when you're looking through the scenarios that were generated, some of them were meek and mild, and nicely, all the bad things that happened were nicely spaced apart so that the resources that were being applied to them were not stretched. Others were absolute, Lucifer himself couldn't have come up with anything worse. They were banging across really major things on top of each other to stretch the resources in a location to the absolute maximum, and across the state as well. Most, of course, were somewhere in between those two extremes, but that was the great thing about doing a 1,000 scenarios, so we could see all the different extremes. So then what we did is we moved over to Stream 3. Now Stream 3 was to worry about how we would react as an organisation, how QFES would react to those scenarios as they occurred over the 10-year period, based on the current state, obviously, so where the assets and the people and the equipment currently are, and then modified by various capital and operational plans. So we can test a potential capital and operational plan by running it against those 1,000 scenarios and seeing how many times our local areas ran out of resources, and how often the state ran out of resources and had to put up its hand and ask New South Wales or Northern Territory or the federal government to come in and help out, and how often the resources overall were being utilised in each location as well. So we decided to, as a demonstration within the 14 weeks, do 3 different capital operational plan scenarios. One of them was the do nothing. So what would happen if we just stuck with the current capital and operational resources as they are located at the moment, and we just replaced so if someone retired, we replaced them. We kept the current skills in place where they are. We kept the current assets and equipment in place where they are. So we did that one as like a baseline, and then we went with a couple of other as demonstration ones as well, with differing levels of investment at differing times. But the idea was that we could assess how well the organisation was able to handle the 1,000 scenarios based on the various capital operational plan scenarios, options I should say, to keep it separate. So what that meant was we had to run in total 3,000 service demand simulations, utilising the assets, people and equipment that were put in place as a result of the current state and the planned changes of those particular capital operational plans of that 10 years. So once we had that, then we had to assess it. So how did we do it? Well, firstly, we had to come up with adequacy standards, and amazingly enough, QFES did not have adequacy standards other than responding to a structure fire within a certain number of minutes in certain locations, and a general guidance, not an actual adequacy standard of similar responses for other areas. But for many of the service demands, there were no adequacy standards, so we had to generate quite a few of those using our experts. And then what happened was we then worked out how often each of the areas were able to hit their KPIs by SA2 by plan, and for the entire network by the plan. Now, what you might have understood by the simulation is, well, hang on, there's 750,000 service demands in each of those 1,000 scenarios. Who's dispatching the actual resources? Well, as it turns out, we had to write an AI algorithm which captured the FireCom dispatch standards, and what that did is it read the service demand. It then dispatched the resources available to it to the location. If the resources that were required were not available, it then looked at the next most close location to see if it could find them there, and so on until it got the resources it needed, or it found no resources and had an entire network exhaustion. Each time that it ran out of resources in a location, it recorded a location exhaustion. But then what it did is it tracked those resources. So it tracked how long it took to get to the service demand. So that was one of the aspects that Stream 2 provided, was the location of the service demand. So that the resources went from their location to the service demand location. Then based on some once again stochastic areas about how long it would take to actually meet those service demands. So we had some standard amounts of time for various severities of service demands, but then there was variations around those. So they were also varied as well. So then those resources would meet that demand, and then they would return to base, and they would be tracked back to that base. So if another service demand occurred in the area, those resources were not available because they were already deployed at somewhere else. So the AI did the dispatching and also monitored the resource availability to be able to meet the scenario's demands as it went through over time. So by the end of the 10 years for each service demand scenario, we were able to say for every single location in Queensland how often it ran out of resources, how utilised its resources were, and we could also give how many times throughout that 10-year period the entire network got resource exhaustion as well. So resource exhaustion was something that was introduced by the project to allow us to be able to do these adequacy standard assessments. So who was actually involved in the project? Who ran those 3 streams? So we deliberately ran those 3 streams in parallel. We only had 14 weeks. So I had a number of resources available to me. Data Analytics was running the show. QFES, I wanted to have as many of their team involved, so that because we needed to hand this model over to them, so that they could run the model and enhance the model going forward. Deep Connect was a data science organisation that I'd worked with previously from Melbourne and Adelaide. So they looked after Stream 1 with data analytics oversight. We had Department of Housing and Public Works who got involved in Stream 3. We had data analytics essentially also not only ran the entire program but also Stream 2, writing the code for the stochastic generation of the scenarios, with assistance by a QUT PhD intern who was working with me. I was trying to help QUT by developing one of their new PhD data science interns, Dr. Paderi Paramita. Then there's the University of Adelaide, who provided quality assurance over the outputs and the deliverables of the project, and did a review, and also provided some advice as they went along, because they've done not quite exactly the same work as this, but similar enough that they could bring along some of their expertise. On top of that, we had within Queensland Fire and Emergency Services, there is a bushfire modelling team, and they were invaluable as well, and they actually sat on the program board as well, that I was the secretariat of, and so obviously QFES executives were the people primarily on that board. So that gives you some idea of who was involved. Next, what data did we use? Now, a lot of this data was primarily used in Streams 1 and 2. Stream 3 was primarily an assessment of the various capital and operational plan options. But there's the National Exposure Index System, Nexus, which was very useful in helping us understand the exposures and how vulnerable they were. Nexus, which is very confusing, was the new HR system, which had a lot of information about where all of the people currently available to QFES were located and what their skills and capabilities were. There was the Emergency Service Dispatch System, which is essentially gave us a 10-year record of what the dispatch people were had done in various places in the last 10 years for various different service demands. So we were able to use that to teach our artificial intelligence algorithm to mimic that behaviour, and also the people from that area were invaluable in helping us polish up the AI in terms of its outputs and the reasonableness of them. The QFES incident record, which helped us understand the outcomes of the last 10 years of service demands, and also helped us understand the frequency of various types of service demands, and also gave us some of the understanding of the severity distributions as well, which we needed to use to generate our stochastic model. Earthquake probability models, we managed to get this one from Geosciences Australia with a very tough promise that we would not publish it, and we haven't published it. I'm not actually sure whether Geosciences Australia has actually published it yet or not. They probably have, but we were able to utilise that. No way we were going to be doing earthquake probability models ourselves, and we were very pleased to be able to get those into the system itself. As it turned out, we had no earthquake experience in Queensland, so we had to use our experts in QFES to come up with what the likely service demands were from those generated earthquakes. There weren't many. I can't remember the exact number, but it was less than 10, I think, overall scenarios had any earthquakes in them at all. Obviously the GNAF, which helps us understand when we have road problems where our services are coming from and where they're going to. That was very useful. The QFES bushfire simulation model data was very useful, and also we wanted to make sure that we had the same assumptions as they had, so that we were using similar assumptions. We didn't want to be going up to the Commissioner with different outcomes for those areas where the two models intersected, and trying to explain why they came up with different results or different recommendations. Obviously, we had lots of wind, cyclone, climate observation data from the Bureau of Meteorology. SA2's geospatial boundaries are available. We had traffic data from the Department of Transport and Main Roads. I don't believe that one was particularly open data, but we were able to get our hands on it because we were working within the Queensland Government. Obviously, the road data is public data. We had local government planning data, which we were able to trawl from the internet, and lots of other minor data sets. What we didn't do was put up with big gaps in our data. If we didn't have the data, we wanted to make sure that we used expert opinion wherever we could to make sure we had a full and complete picture. We did want to say, oh well, we were able to do the whole lot, but we left out terrorism. Sorry, just have to presume that uses up none of our resources, which is just not appropriate. So what we had to do is we had to go and run workshops and get the best opinion of various stakeholders about whether or not terrorists would impact us. So just going over Stream 1, we used self-organising maps, and this was Deep Connect's area, and that was able to identify some very interesting characteristics. Obviously, the age of structures was very important, the material they were made from was very important, the density of the housing was very important. After all of those very obvious factors, then we also found that the socioeconomic status was also important. So it could be that those people with lower levels of income and employment may not have the resources to be able to avoid fire quite as much as others, with all other things being equal. We don't actually know what the reason is, but we put it into our model because that's what the data was showing us. Interestingly enough, we weren't able to show up to that point in time, so we had up to July 2018 data. We weren't able to show that there'd been an impact of climate change up to that point in time. So we had to rely on our experts' opinions about how that would change. Some of the outputs, so this is actually generated by Stream 1, and this was assessed against the actual observed data to see how closely it followed that. So we obviously false alarms is the most frequent thing. They are very rapidly dealt with, but they're still very frequent. And unfortunately, mobile property crash, which is essentially means a road crash, vegetation fires, and so on, are the most frequent. And as you can see, they do change seasonally. But quite a number of the others are also there if you're interested in having a look. The more interesting stuff was the major events seasonality, which was very heavily modified into the January through March months, but things like earthquake are very low probability and very consistent, and they change to be quite insignificant through July through to September. And this was checked against our experts and against our historical incident data to see if these generated probabilities matched up with their experience, and it did. One of the first questions that was asked by the Nicole Lott, who is the head of QFES Futures, director of QFES Futures, was, well, what if I wanted to change the scenarios about the risk factors? So, for instance, she was saying, what if we decide to spend some money on improving the quality of the alarms, and therefore we would expect a reduction in false alarms? Or what if we felt that climate change was about to extend the bushfire season? So I had to make it such that it didn't require data scientists to be able to modify these kinds of factors. So we came up with an Excel input system, which basically said if everything's a 1, that's the default that's come out of the analysis that the models from streams 1 and 2 have come up with. And if you want to modify what streams 1 and 2 come up with to generate new scenarios with different probabilities, you can use this input factor to do that. So you modify the spreadsheet, press the button, and up it goes, modifies the probabilities, and then you run the stochastic generation algorithm, which we left with QFES, to come up with the new scenarios. Alright, so this one here is an extension of the bushfire season. So we're presuming that in February we're going to get a 20% increase, so that the bushfire season increases into February, but goes back to normal for March, and similarly gets bigger in August earlier. So they could have made that too if they wanted to say it's doubled, but that was an example where we'd have a 20% increase in those 2 months to extend the bushfire season. And similarly, they could say that if they wanted to make the bushfire season more severe, they could increase the numbers during the actual bushfire season. So say they wanted to make December twice as bad, it's already pretty bad in December, but they could write a 2 there, and that would double the severity of the December. And that was both in terms of the frequency and the severity. So we had various distributions of each of those things to do an extension. We tried to make it simple so that the executives were able to do it, but what that means is like a lot of the complexity is hidden away underneath. And we do have the data scientists who can help modify those things further down if it's required. So here's the false alarm reduction investment approach. So this is where that if Nicole wanted to spend a few $1 million on going around and inspecting the alarms in properties to try and get a 20% reduction statewide, then this is what they would do across the whole year. Okay, so Stream 2, the 1,000 scenarios. So yeah, 600,000 plus. That's a bit wrong. It's more like 700, 750 in the end, as we kept on adding in more and more service demands. And I think I've already described how some of them were absolutely horrible, and that the dispatch rules were what was used. We didn't do the whole thing. We did Rural Fire Service and the Queensland Fire Emergency as well, but we didn't do the State Emergency Service. We didn't quite have the incident data and the asset data from SES quite as well. So that was one of the opportunities that the new QFES team, which we helped create, would be able to take this model forward. What we were surprised about was how little major events had on the acute emergency network we were modelling. So we were quite surprised that when Cyclone Debbie came down the coast, there wasn't the massive increase in emergency response that was coming through these kinds of models. In fact, what ended up happening was a lot of the latent capability within QFES, so people who are working as executives, or people who'd recently retired, or people who were training, or people who were being trained, were often pulled off doing their training, or from their retirement, or from their holidays, or whatever it was. So not being part of the acute response network, and they were the ones that came in to respond to the big emergencies, along with a very large volunteer workforce. So we were all surprised, including the strategy people, about there was some impact of these large emergencies, but not as much as we thought there would be to the response, to the actual emergency acute response. So as a result, once again, we introduced that into the QFES thinking as well, separating out the acute emergency network from the major disaster response, which was a different kind of thing. And I think that was a major contribution of the project to the strategic thinking of QFES. So here's an actual simulation. This particular one is an extract from one of the 1,000 scenarios. We were particularly interested in this one because it created a network exhaustion. What we would have to say, though, is this is not really part of the model. This is more about visualizing the model so us humans can understand what's going on, what the AI is doing underneath it all. So we're running, if you can imagine, we're running through one of the scenarios, service demands are being generated, and then the AI is looking for resources, dispatching them, and so on. So let's see what happened in this particular case where we got a resource exhaustion. All right. So if we're having a look, we can see where all the locations are. We've got, there's our service demand. It needs 32 people, 7 vehicles, and 2 hazardous material experts, which is, now that's a big simplification. As I said, this is just a visualization for us humans. There's obviously a lot more than that. So firstly, it exhausted the Bundaberg fire area, and then went looking at the 2 most close fire appliances or areas. Found 9 people and 2 trucks in one, and 5 people and 1 truck in the other. Well, it found a person there without a truck. I don't know how the person got there, but it looks like we may have found enough people for the fire, but we're still looking, by the look of it, for the hazardous materials officers that aren't in the area. So we're looking wider, we still haven't found any, and now we're looking across the whole state and we haven't found any. So obviously the hazardous materials officers were otherwise deployed somewhere else at this particular time. But what this does is it demonstrates what the AI is doing very, very rapidly, obviously, vastly slowed down, and then visualized using the ArcGIS Esri tool, so that us humans can see what's going on in those 750,000 service demands in those 1,000 scenarios. And what this does is it builds the trust in the model. Very important part of this whole project was making sure that we build the trust of the executive. We didn't want it to get to the point where the model, computer says go or computer says no, and so therefore they just trust the computer. So the computer says we should put resources in this place or that place, and that's absolutely right. No model is perfect. These models only help explain things, and it should be used to help decision making. But the other extreme was that they thought this was just a load of rubbish and wasn't close enough to reality to be useful, and therefore completely reject it. So we were constantly trying to walk that fine line of building the trust in the model, but not to the point where there would be too much trust. Another point was that QFES was very pleased with this outcome. Amazingly enough, I presented this to the Commissioner and her executive team in October, and roughly 15 weeks after we started. And only about 3 weeks later, a major fire broke out in Bundaberg to start that eventually spread across the whole east coast of Queensland and became the most major bushfire that Queensland has had to deal with. Obviously, we did not know that was going to happen, but it was pretty amazing that the scenario that we ended up showing the most senior people in QFES happened to be the one that ended up occurring. I promise you, we did not start that fire. The key is that we wanted to make sure that it was objective. We wanted to make sure also that QFES was able to take this model on its own going forward. Now, they were so pleased with it, they made funds available to grow the Coles team to come up with a permanent data science team within the area. So we helped come up with an operating model for QFES's new team. We designed the position descriptions, helped them with the recruitment and selection, and found 2 permanent and 1 temporary data scientists to help them to flesh out this model, make it better, and also to maintain the model going forward, as well as go into a lot more areas that data science could help QFES in. We left them behind a roadmap of improvements to the model, and that basically helped these new staff members. And at the same time, we were mentoring a couple of the team who were working within the program for us, so that they had a lot of understanding of the model, built a lot of skill sets, and a lot of it's a lot of the attitudes that data scientists have. that we were helping to imbue within the data analysts that were available in the strategy team in the first place. So they now have a fully functioning and data science team that's doing some great work now, and we're very pleased to see that happening. But that is part of the whole thing. You've got to make sure these things are sustainable and create continued value. Anyway, I think that's enough. That pretty much describes what it is that we do here in data analytics. And if you want to know more about it, or you think that this might be something useful for your organisation, don't hesitate to contact us. Bye for now.